All right, so in this lesson, Understanding RF Mathematics, it's not a very long chapter, but there's a few things that we'll talk about here that are pretty important. Basically, the whole goal of this chapter is to understand what kind of math is involved when we're dealing with Wi-Fi and understanding the difference between different ways of evaluating different concepts within the Wi-Fi environment. So we're going to go through this lesson. We'll talk about common values that are used to describe power in a wireless network or particularly a radio frequency environment. Measure of watts, measure of milliwatts, decibels, and how we can reference decibels. We'll talk about the concept of power in terms of the decibel in reference to a milliwatt and the power of signal compared to the power of the antenna, which is going to involve some calculations, and we'll talk about those calculations in terms of the laws of 3 and laws of 10 when it comes to logarithmic computing, and describe a decibel reference to the isotropic antenna. An isotropic antenna, we'll learn this a little bit later on, is essentially a perfect antenna, a point in a sphere, I guess you will say, referring to a power gain relative to that particular type of antenna. And then we'll take a look at the effective isotropic radiated power, and look at various antennas, compare their ability to concentrate the flow of energy into a particular direction, because we have omnidirectional antennas, we have patch antennas, we have very focused dish or Yagi antennas, so we'll talk about that. And then we're going to finally take a look at how to understand and calculate different RF math problems to calculate the correct antenna in each situation, because antenna sizing, antenna placement, antenna choice is a very important concept to understand. And we're going to take a look at all of these concepts in this particular lesson. Okay? Some stuff that you see in here is something that you've probably already been exposed to. But I will say this, if you are planning on going on and taking the exam a little bit later on, this is definitely something you're going to have to know, because they do ask quite a few questions on the exam related to these math concepts. All right. So a key problem in a wireless network design is to determine how much power you should have or you should use when you're sending traffic from the source to your destination. And that's going to be based on the overall deployment model. Am I trying to reach an individual host across a long distance? Am I trying to reach a range of hosts within a large geographical area, and so on? The distances that can be achieved depend on several different factors. When we talked about this in the last lesson, where the beam width or the focus of the energy will determine how far away the actual endpoint can be. The power that's being sent from the source will determine that as well. The type of access point, the power settings on the AP, and so on. A common misconception that I see a lot that people use when they're deploying wireless networks today is they say, well, if my AP supports 100 milliwatts, why not just transmit on 100 milliwatts, right? And oftentimes that's not the case. You in fact want to try to transmit at the lowest possible power or a minimal power rating to maintain your connectivity needs, because you want to be able to adjust that power up if needed for loss of another access point within the grid or whatever. But you don't always want to transmit at the maximum power level. It's a pretty safe bet to say that the higher the output power of an AP, if nothing else changes within that system, the more distance that signal will go. But that can also cause additional interference with other cells in the network and so on. We see this a lot. Customers put access points in the warehouse. They think one of two things. They either think, well, I'm going to save money by putting fewer access points at higher power, or I'm going to ensure connectivity by putting as many access points as I can in a small area. That introduces two different problems when you're dealing with these deployments. If you have a small number of APs deployed in a large space, in other words, you're deploying large BSAs, That means you typically will have more clients within that basic service area. And remember, this is a shared access or shared resource. So you are in the case of more clients within a single BSA, those clients are now competing with each other for that frequency. Remember, this is a contention-based network. Now, the other scenario that I described was besides having a single AP with the power turned way up, so you have a large basic service area, that will give you additional coverage area, like I said, but again, you're going to have more clients competing within that small space to gain access to the network, and that can actually slow down those clients because they're competing in a contention-based architecture. The downside to adding density to access points, in other words, saying, okay, I'm going to make sure that I have enough coverage, so I'm going to put 20 access points in this small area as opposed to 10, means that now you have more and more access points that are competing for only a certain number of channels that don't overlap in the wireless space. When we get into the radio frequency analysis and radio frequency design, I'll talk about that. But there's in 802.11g, which operates in the 2.4 gigahertz spectrum, there's only 3 frequencies that don't overlap. So if you have a bunch of access points put into that small space, you're inevitably going to run into a situation where you're going to have access points competing with each other, and you're going to get co-channel interference. So it really is a balance of access point placement and access point power. Power being a critical component to that, which is why I kind of got off on that side chart discussion, because that's what we're talking about here. The distances that can be achieved in coverage will depend on the power, but just increasing the power is not always your best option. The first unit of power that's used in the measurement of any wireless system is the watt, and it's also used in many other systems as well. Named for James Watt, the watt is a measure of energy that is spent or consumed per second. So 1 watt represents 1 joule of energy per second. You can kind of see that depicted in the diagram. If I move 1 kilogram of weight over 1 meter, that requires 1 newton of force, because that's what a newton is defined as, 1 meter per second. So a joule is essentially the amount of energy that's generated by a force of 1 newton moving 1 meter in one direction. A newton is the force that's required to accelerate 1 kilogram at a rate of 1 meter per second squared. Now, we of course don't use these types of measurements when we're dealing with wireless communication, but we can extrapolate this information because we typically deal in milliwatts when we're talking about dealing with wireless transmissions and radio frequency transmissions. A typical AP can have a power of about 100 milliwatts. In fact, you're going to find that the overall effective isotropic radio power that's permitted in the United States is about 100 milliwatts. So there is a calculation that we're going to show you in this lesson here that allows you to describe the output power of the access point, the gain of the antenna, and the loss of the cabling to calculate that value. Does that make sense? So many different ways of representing these values, and that's where it gets a little bit confusing because of the way these values can be represented, but and the unit of measurement that we use for these. But I'll go slowly here, and if you guys have any additional questions, you can certainly ask. Okay. Probably another, well, not probably, definitely another common reference that we use in referencing power and consumption and whatnot is a decibel. This is a unit of measurement used to express essentially the ratio of one value of a physical property to another on a logarithmic scale. So we're comparing 2 different values on this logarithmic scale. It can be used to express a change in value, plus 1 dB, for example, or minus 1 dB, or it can be used to describe an absolute value. Okay? In the case of describing an absolute value, it expresses a ratio of a value to a reference value. In fact, we always use a reference value in the case of wireless. We'll talk about what that reference value is in a minute here. Okay? When it's used in this way, the decibel symbol should be appended with the suffix that indicates the reference value or the property of that value. So you'll see, for example, a dBm for decibels in reference to a milliwatt, or a dBd, or a dB, just a dB. All right, we'll see some examples of this a little bit later on. I mean, you can reference it in many different ways. A dBV, for example, is a decibel in relation to a volt. dBm is a decibel in relation to a milliwatt, and so on. There are two different scales used when expressing a ratio in decibels, depending on the nature of the quantities, field power or root power, and we're going to take a look at essentially field in our case. But when we're expressing power quantities, the number of decibels is 10 times the logarithm to the base 10 of the ratio of the two power quantities. That sounds like a very confusing way to say it, but that basically means that a change in the power by a factor of 10 corresponds to a 10 dB change in level. So we see that identified here. Actually, the 1, 2, 3, 4, fifth bullet point down, 10 dB is 10 times the power. When we're expressing the in field quantities, a change in amplitude by a factor of 10 corresponds to a 20 dB change, but that's not what we are doing in this particular case. We're doing it as a ratio of power. So you'll see here 0 dB is the same power, whereas 3 dB is 2 times the power, minus 3 dB is half the power, 10 dB is 10 times the power, and minus 10 dB is 1/10 of the power. There are other ways to evaluate these field quantities and power quantities and whatnot, but those are essentially the ones that we use in a wireless environment to represent the values that we're going to represent in our wireless environment. So we'll take a look at some examples in this lesson and describe, what that represents. A milliwatt is an absolute power value. It simply expresses the amount of power consumption by an endpoint or a device. So oftentimes we're trying to use this in comparison from one device to another. And like I said, the dB is another way that we commonly represent power levels in a Wi-Fi network. Calculating decibels can be challenging because it depends on how you're looking at those decibel values. So you might go online and say, well, I can't remember what Scott told me about calculating these decibel values, so I'm going to go read a document about it. But if you're, like I said, if you're referencing that in, terms of, one type, in other words, a field or a power, it might mean one thing, right? Power quantities, 10 times is, or plus 10 is 10 times the level, or 10 dB change. But if you're looking at it in the terms of field quantities, it's 20 times. So you need to make sure that you're looking at something that's relevant to what you're actually trying to calculate. What you see on the slide here is what is used in a wireless environment. The term decibel actually derives from the term bell. At the beginning of the 20th century, Bell Laboratories needed a value to represent loss in a telephone line, so they invented this bell to represent the typical loss from their lines over a 1 mile period. And then that became kind of a standard later on in describing this loss, right? So a decibel is 1/10 of a bell, deci being 10. A misunderstood part of the decibel concept is that it is a relative value. For example, a 1 bell loss was a loss over 1 mile compared to the original emitted sound level. So you would always have to know what was the original value that you were dealing with. Well, in wireless, we don't really know that. In fact, oftentimes the original value is not known. So it becomes more of a relative value instead of a physical value. If we're talking about decibels for sound, the reference level is the minimum sound that a human ear can perceive. All other sound levels are compared against that particular reference point. So this is what I had mentioned previously. When we're dealing with decibels and measurements, we always try to identify a reference point, right? Some sort of reference value. And we'll describe what that reference value is in a wireless network a little bit later on. Because decibel is a power scale, it can be used to compare sound to anything else. It can be used to compare hertz, joules, voltage, watts, milliwatts, etc. So a dBm is a milliwatt reference, a dBV, like I said, is a volt reference, and so on. The decibel scale is logarithmic, so there's a progression that takes place. 0 dB is a measurement of 0 dB based on, well, that becomes essentially my reference value. Decibels compared to one value to another, where 0 is essentially the reference point. If the value that's compared against the reference is 0 dB strong, then the value has no more or no less strength than the original reference. Both values become the same. All right, now we see that on the curve here, although it doesn't fall exactly on the 0 point. We see it on the curve here represented as the P2 over P1. 10 dB, when the power is 10 dB, the compared value is 10 times as powerful than the reference value. What if it was 20 dB plus 20 dB? Well, we're going to go through some examples where we talk about that. Of course, that would be 20 times as powerful. 30 dB would be 30 times as powerful, and so on. It's just a simple multiplication, right? If the value is 10 times less, it'd be minus 10 dB. 3 dB represents twice as powerful. So 6 dB would be 4 times as powerful, not 6 times. And 9 dB would be 6 times as powerful, and so on. We'll go through some examples and we'll do some calculations. There is a, this is a concept that you're definitely going to have to know for the exam. 10 dB is pretty easy to work with, right? It's 10 times. 10 times the power, 20 is 20 times the power, 30 is 30 times the power, and so on. When you're dealing with that 3 dB, though, you just have to remember it's 2 times the power, twice the power. All right, so 6 dB plus 6 dB is 4 times as powerful as the output device, or as the initial device. 3 dB increase indicates that the second device is twice as powerful, and so on. If we follow that same logic, 9 dB means that the second device is 8 times as powerful, because we go 2, 4, 6, but it's powers of 2. It's logarithmic, right? So we can't say that 9 dB means that the device is 6 times as powerful, because it's 2 times 2 times 2. Does that make sense? So 2 times 2 is 4 times, and then 4 times 2 is 8 times as powerful. You don't simply add the power levels, you multiply the power levels. So 20 dB would be 10 times, and then it would be times 10 again, which would be 100 times, if that makes sense. We'll go through some examples. A power increase of 9 dB means that the second device is 8 times as powerful as the reference source. If 3 dB is twice as powerful, if we add another 3 dB, that's 4 times as powerful. Then another 3 dB, like I said, increases the power by 2 again, making it 8 times as powerful. We always deal with this when we're dealing with powers of 2 in binary as well. It's not just simply increasing by double. Like I said, on the exam, you're going to have to be able to calculate some of these values. And that's going to be a very important concept to understand. They'll give you some numbers, and you'll have to be able to calculate what those numbers represent. I'll see if I can go through some examples. I think we have a discovery where we kind of go through some calculations as well. All right. Decibels are used obviously in defining Wi-Fi networks to compare powers, input power versus output power and gain, etc. Two types of powers that can be compared are the electrical power that we send by the transmitter, which is our active gain, right? And the power of the antenna, which is our passive gain. So we have our initial power that's being sent by the access point, and then we have our passive amplification by the antenna, which is the gain of the antenna. Because the signal that a transmitter emits is an alternating current, we described that previously, the power levels get expressed in milliwatts. Comparing powers between transmitters is comparing milliwatts. So because the reference is milliwatts, we reference power in terms of dBm. dBm meaning decibels reference to milliwatts. There are some rules that you have to follow when you do this. All right, and let me switch the, well, I'll leave it on here for now, but there are some rules that we have to follow as we go through this process. Any device that sends a 0 dBm, that stands for a decibel in reference to 1 milliwatt. That is our reference, by the way. It's always 1 milliwatt. So this is the key right here, right? It's always in reference to 1 milliwatt. Sends the same amount of milliwatts as the reference source, meaning the power reference is 1 milliwatt, so the device sends 1 milliwatt. Does that make sense? I hope that makes sense. It can be very, very confusing, but just think of this as your base point or your reference point. Okay? A device that sends 10 dBm sends 10 times as much power than the reference source of 1 milliwatt. So it sends 10 milliwatts. Minus 10 dBm is 1/10 of the power, so 0.1 milliwatts, and so on. That goes back to our previous slide here, where plus 10 is 10 times the power, minus 10 is 1/10 of the power. So they're not going to ask you on the test, hey, if I'm sending at 10 milliwatts or 10 dB, what's the power? That's going to be too easy to calculate. They might say I'm sending at 33 dB, or I'm sending at 36 dB, or I'm minus 36 dB, and so on. And then you have to calculate based on those values. We'll take a look at some examples of that. So 3 dBm, again, like I said, is twice as powerful as the reference source. So that's going to be 2 milliwatts if the reference is 1 milliwatt, which it always is. That's a constant that never changes. A device at minus 3 dBm is a half a milliwatt. So a device at 6 dBm sends 4 times the power. So adding 3 dBm, excuse me, makes it 2 milliwatts. Adding that again, or multiplying that again times 2, makes it 4 milliwatts. Make sense? When I finish with this particular section here, we can put some on paper and see if we can do some calculations. But it's pretty straightforward if you follow the 3s and 10s rules. So the rules 3 and 10 allow you to just basically kind of determine the transmit power based on the gain or loss in dB of the overall system, right? For every gain of 3 dB, we multiply by 2. For every 10 dB gain, we multiply by 10. If it's a minus 3 dB gain, we divide by 2. A minus 10 dB gain, we divide by 10. So these rules allow us to perform really kind of basic calculations. Obviously, maybe the gain is not exactly 10, maybe it's not exactly 3, maybe it's 4, maybe it's 5. And there are ways to calculate those values as well. Obviously, on the scale, there are numbers that associate to that power level, those power levels. But for the purposes of this class and the purposes of the exam, the 3s and 10 rules are really all you need to know. They're not going to give you a dB gain of 12. Well, that would actually work. They're not going to give you a dB gain of 22 on the test, right? Where you can't calculate to the 3s and 10s. 12 would work because you could do 3, 3, 3, and 3, right? But you couldn't do 10 and 2 because you don't know what the reference is or the multiplication is for the 2. So you would just do 3, 3, 3, and 3. All right? All right. Let me see if we have some examples. You know, there is, I don't know if you guys have the official courseware or not, but in the book they do have a table that kind of references values in between those values, right? For example, minus 20 dBm. Now that one's an easy one to calculate, right? Because minus 20 dBm in reference to the milliwatt, being 1 milliwatt being 0 dBm, so we multiply that times 10, so it goes to 0.1, and then multiply that again times 100, that goes to 0.01, and so on. So there are obviously ways that we can calculate this based on those values, based on those numbers. And of course, minus 3 dBm is a half a milliwatt, and minus 6 dBm is minus 6 dBm is you know, again, twice that, right? So let's look at some examples on the conversions here. To convert decibels referenced to the milliwatt, the dBm, to milliwatts, we calculate that each addition of 10 multiplies by a power of 10, and each addition of 3 doubles that particular result. All right, so let's say that we have 36 dBm. Our reference is always 0 dB, which is 1 milliwatt, so we multiply that times 10. That gives us our first 10. Then we have to do another 10 to get us to 20, plus another 10 to get us to 30, plus 3 to get us to 33, plus 3 to get us to 36. So if you add up these numbers, of course, that's going to equate to 36 dBm. Beginning at 1 milliwatt, we multiply, apply our rules of 10 and 3s, multiplying or dividing by 10, or 2 based on the value. So 1 milliwatt times 10 times 10 times 10 times 2 times 2 equals 4,000 milliwatts, or 4 watts. Make sense? 27 as an example. Now, 27, I can't get by doing 10 plus 10, 3 plus 3, because I would have some leftovers. But I could do 30 minus 3, if that makes sense. So again, starting at our 1 milliwatt reference, we multiply times 10, which gets us to 10 milliwatts, multiply times 10, which gets us to 100 milliwatts, multiply times 10 again, which gets us to a watt, or 1,000 milliwatts, and then minus 3 dBm would be to divide by 2, which gets us to 500 milliwatts. All right, and that's a pretty basic calculation if you follow those rules. And like I said on the exam, they're not going to, if you do decide to take the exam, they're not going to give you some crazy number. They're going to give you some number that you can actually calculate. All right, and it always works out to be the same. Okay, always works out to be the same, and they'll always kind of give you a good place to, you know, an even number to calculate, I guess I should say. All right, to convert milliwatts to decibels in reference to 1 milliwatt, which is a dBm, again, decibels to milliwatt, so we write that as a dBm. We have to first determine whether the value that you want to convert can be divided by 10. Obviously, the goal here is to get some value that is as close to 1 as possible. Now, that may not always be possible. Certainly, 40 we can do, and 50 milliwatts, it's not as easy to do, right? So it's kind of like a little juggling act. You're trying to kind of figure out what numbers to use, right? So let's take a look at these examples here. Let's take a look first at the 40 milliwatt example. You can divide 40 by 10 one time. So 40 milliwatt contains at least 10 dBm, but you cannot divide the result of that division, which is 4 by 10, and achieve a single integer, right? But you can divide 4 by 2, so that would be to add 3 dBm. And you can also divide the resulting value, which is 2 by 2, so add another 3 dBm. Does that make sense? So remember, 3 dBm is a multiple of 2. So in this case, we're doing 10 times 2 times 2. So the final value would be 10 dBm plus 3 dBm plus 3 dBm, because remember, plus 3 means to multiply by 2, and plus 3 means to multiply by 2. So 10 times 2 is 20, 20 times 2 is 40, which is equal to 16 dBm. In another example here, we have 50 milliwatts. We can divide 50 by 10 one time, but the remainder is 5. And that's, of course, not divisible by 2. So another method that we can use is to double the number and then do the math. 50 milliwatts becomes 100 milliwatts. Or express the 100 divided by 2 and so on. So 100 milliwatts is 10 times 10, or 20 dB. Now you need to divide by 2 because you doubled that initial value of 50 milliwatts. So if you divide, you have to subtract 3 dBm. So the final value is 10 plus 10 minus 3, which is 17 dBm. Okay? Does that make sense? That one can be a little bit more confusing, but my suggestion would be to go ahead and practice a little bit. If you know, obviously this is not something that you're probably going to have to concern yourself with too much when you're deploying wireless and managing wireless in a gosh, what can I say, in a normal environment, right? You're not running around calculating dBMs and dBds and all that stuff, but or dBs and whatnot. But you know, for test purposes, it's certainly something that you need to know. Okay. All right. There is a direct formula for doing the conversions. It's not the 3s and 10s rule. It's dBm is equal to 10 times log 10 of P times the milliwatt divided by 1 milliwatt. But P is power, of course. But we don't typically use that formula in this class anyway. They do ask a lot of questions on the test about this math, though. There's no doubt about that. Definitely. All right, so the next thing that we're going to talk about is a dB in reference to an isotropic antenna. Now, an isotropic radiator is a theoretical point source of an electromagnetic field or energy, which radiates in the same intensity of radiation in all directions. It has no preferred direction of radiation. It radiates uniformly in all directions over a sphere centered on the source, and it's kind of depicted as a point with a perfect concentric circles leaving, or spheres leaving that point in all directions. They're used as reference radiators so that other sources can be compared to them. So for in the case of wireless, we're using it to determine the gain of antennas. And a coherent isotropic radiator of electromagnetic waves is really not technically possible. It's a theoretical antenna, because why would it not be possible to have a coherent isotropic radiator? Because you can't have a radiation source without some sort of connection to it, right? A cable, a connector, whatever it might be. So at some point, you're not going to have some radiation. Your information's not going to be radiated because it's going to be blocked by that connector or whatever. The isotropic antenna, which is what we use in antenna theory, is a hypothetical antenna radiating the same intensity of radio waves in all directions around the antenna. So it has a directivity of what we call 0 dBi. dBi is a measurement used to reference in a reference point for antennas, and the little I stands for isotropic antenna. So if you ever see a dBi, you notice that this is a decibel measurement in the terms of that isotropic radiator. In reality, radiators of linear polarization are impossible. Like I said, the radiation field cannot be consistent with any of the equations in all directions simultaneously because you have a source of the information or the data. But if we do consider a large sphere, like we see depicted on the diagram here, surrounded by a hypothetical point source, the radius, the wave over a reasonable area is going to be spherical and uniform. That's that isotropic radiator. And there are many, many calculations involved in calculating these radiators. But let's talk about what the necessity of having these in reference to antenna theory is. So a dBi, like I said, is a decibel in relative to an isotropic antenna. This is going to refer to power gain relative to that isotropic antenna. Very useful in many scenarios when you need to compare powers of antennas. In fact, when you go look at antenna gain and you compare the antenna power, it's always going to be in reference to dBi, or it could be referenced to dBd. We're going to talk about the relationship between dBi and dBd in a minute here. An antenna doesn't actually send an electrical current. An antenna sends an electrical and magnetic field. If it sent an electrical current, that wouldn't be it'd be very painful if you were standing next to it, I suppose. So as a network engineer, as a Wi-Fi engineer, you have to have a tool that compares the power of the antenna without using the indirect value of the current that's being sent by the actual access point. So a reference antenna was created for this purpose. The antenna is a spherical antenna, one dot large, meaning that a point in space, essentially, that theoretically radiates in all directions. Again, like I said, you can't really have this exist in the real world because one dot large is almost impossible to produce. Something would have to be linked to that antenna to send current to it. And an antenna also doesn't actually radiate equally in all directions because the construction is not perfect, which means that you're going to see imperfections and so on. But, you know, this is a theoretical antenna. It's called an isotropic antenna because it radiates equally in all directions. The scale that's used to compare the powers that the antennas radiate to an isotropic antenna, remember when I said we're talking about dBs, we're always talking about dBs in relation to some other reference. dBm is a decibel in reference to a milliwatt. dBd is a reference into decibels. dBV is a reference to voltage. dBi is a reference to isotropic. The logarithm progression of the dBi scale uses the same rules as the other decibel scales. 3 dBi is twice the power as a theoretical reference antenna. 6 dBi is 4 times, 10 dBi is 10 times, and so on. So the laws of 3s and 10s don't change in this particular case when we're referencing an antenna referencing antenna gain based on an isotropic antenna. Another way that we can measure antenna gain is in reference to our dipole antenna, which is one of the most common types of antennas that you will see in wireless today. And this is going to be referenced as dBd. So you can see here, very important number to note, 0 dBd, which is your reference point for your dipole antenna, is equal to 2.14 dBi. This is a fixed value. I'm not sure how they came up with this value originally. I'm sure that there's a reason that 2.14 was chosen. But in reference to dipole antenna, dBd, 0 dBd is equal to 2.14 dBi. All right. So rather than using a theoretical isotropic antenna as our reference point, we can compare our antennas to a realistic antenna, an antenna that's used in the real world. This is the simplest possible antenna. It's called a dipole antenna, and it transmits in essentially a donut shape. It radiates in a donut shape, so you get very little signal above and very little signal below the antenna, but you get a lot of signal out to the sides of that antenna. We'll look at some antenna patterns a little bit later on when we get into the antenna theory. Some companies present the values of their antennas in dBd, some in dBi. It just depends on the manufacturer. Some will list actually both values. It doesn't really matter. Just make sure that when you're comparing two different antennas from two different vendors, that you're looking at the same source, right? The same value, right? Whether you're converting it or not. Make sure if you're going to use dBi that both are represented as dBi. If you're going to use dBd that both are represented as dBd. So 0 dBi is equal to a dBd plus 2.14. dBd is equal to dBi minus 2.14. So if an antenna has a dBd value of 5.4, all right, let me put this in Notepad here. Bear with me a second. So let's say that our antenna has a dBd value of 5.4. All right. Now that expresses the gain of that antenna in the system. So we have our output power from the AP with a gain of 5.4 dBd. We'll find out how to insert this into the whole equation of calculating the effective isotropic radio power a little bit later on. How do we convert this to dBi? So dBi in this case would be 5 minus, well, it would be 5.4 dBd. Again, the D stands for our dipole antenna, plus 2.14, oops, which would equal 7.54 dBi. Now, that number by itself doesn't tell us a whole lot about that antenna. It expresses the gain of that antenna when it's connected to the system, but we'll take a look at how that can be inserted into the overall calculation of the gain of our system. How about another antenna that has a dBi value of, let's say, 13.8? Okay. Well, if I want to make that or compare that to a dBd value or calculate the dBd value, I would subtract 2.14, which is equal to 11.66 dBd. So you'll see this on the test. They're definitely going to give you a calculation to do on the exam to calculate these values. Regardless of whatever measure we use, there is a 6.26 dB difference between these two antennas. So antenna 2 is a little bit more than 4 times as powerful as antenna 1. Does that make sense? There's a 6.26 difference. If I take 13.8 and I subtract 7.54, that's a 6.26 difference. But remember, you have to compare the same values, dBi to dBi. So 6.26 is plus 3 dB plus 3 dB, which is 4 times as powerful. Obviously, there's a little bit left over. We don't really concern ourselves too much with that because we're not dealing in exact values here. The power consumption is what matters when you're determining which antenna to use in a given situation. Remember, an antenna can never create more energy than that already existed, but it can definitely focus that energy and disperse that energy in a specific direction. We'll get into more antenna theory a little bit later on. So one of the components that are necessary to be able to calculate is this value called effective isotropic radio power, or EIRP. Comparing antennas gives you a measure of the gain of the antenna, but that's not our only concern when we're talking about calculating power in an overall system. Remember, the antenna is a passive device, so it doesn't add to the energy it receives from the cable. It focuses the energy, it generates an output based on that energy. The only thing that antenna can do can radiate the power in a particular direction. So we're not adding gain to the energy that was received by the cable itself. An easy way to understand this concept is to take an example of a balloon. The quantity of air inside the balloon is the quantity of energy to be radiated. If the balloon is shaped as a sphere, like an imaginary AP at the center of that sphere, the energy is equally distributed in all directions. Now, take that AP at the center of the balloon, well, assuming that the balloon is a perfect sphere, I guess. Most balloons are not, but you can imagine that that's like an isotropic antenna. But if we press that balloon into the shape of a sausage, and the AP is placed at one end of the sausage, now we're talking about the quantity of the air in the balloon didn't change, but the direction, or where the air is located and where the energy radiates, is in one direction along the sausage, if that makes sense. Interesting example. Okay. The concept here applies to antennas as well. An antenna concentrates the energy it gets from the AP over the cable into a particular direction. It's more powerful in that direction than the antenna radiates energy. If I was to send all that data, if I have a parabolic dish antenna that has a focused beam width and focused energy, it's going to have more energy in that path than an isotropic a dipole antenna that's going to be sending data in multiple directions. All right, so it's a matter of concentrating the energy and so on. So that's a common misconception in wireless design, is that the antenna somehow increases the output power of the system, because we do call it antenna gain. It's a little bit misleading, antenna gain, and it does go into the overall effectiveness of the system based on the transmission, but it doesn't actually increase the power. Okay? Describing the power of an antenna is like comparing their ability to concentrate the flow of energy. The more powerful the antenna, meaning the higher DBD value or the higher DBI value, the more it focuses or concentrates energy that it receives into a narrower beam. So the total amount of power that's actually radiated is not higher, it's just focused. I guess it's kind of like a flashlight, right? You know how you can get those flashlights that you can turn the head of the flashlight to focus the energy? Or a hose, for example. I'm thinking of a hose now with a nozzle on it that can either disperse the water in a much broader fashion, or you can focus the power of the water, or that flow of water, into a single direction. It's the same kind of concept with an antenna. The direction towards which the beam is concentrated, the receiver energy becomes higher because the receiver gets a higher percentage of the energy that was actually emitted by the antenna. That makes sense. So what we have to do as an engineer is we have to be able to determine what's actually being radiated from the antenna towards the main beam, and that is what we call effective isotropic radio power. Very important to understand, EIRP is an isotropic value because it's the amount of power that an isotropic antenna would need to emit to produce the peak power density that is observed in the direction of the maximum antenna gain. All right. In other words, it tries to tell us basically what the isotropic equivalent would be, how much energy is radiated in that beam. So it's not actually effective power, it's just isotropic radio power. Okay? The formula is very simple. EIRP is the transmit power in dBm, so that's decibels in reference to milliwatts. And when you set the power on an access point, you set the power based on milliwatts. Plus antenna gain, which is always based on dBi, minus the cable loss, which is dB. That's our attenuation in the system. So we're using, again, isotropic antenna reference. That's why it's called the effective isotropic radiated power. So it is a very important concept because EIRP is used by federal, I wouldn't say federal, but governing bodies to describe what the maximum transmit power of a transmitter and the final EIRP value is of a system. And you can't exceed those values if you're using the ISM bands. So these are numbers that you may or may not have to calculate. You don't really have to worry about it too much in the Cisco space because Cisco will not allow you to, they don't manufacture antennas that allow you to exceed the overall EIRP that's allowed in the United States. That's why these access points come with country they're country specific because they're designed to meet the requirements of that particular country or region or whatever it might be. Okay. All right. So we have one more thing here where we're going to go through. It's what we call a discovery lab. Very basic concept. We're just going to go ahead and apply some of the things that we've learned in this lesson in this exercise. So in this activity, we're going to work with the formulas that we talked about previously, right? We're going to convert our milliwatts to our dBm and back. And then we're going to take a look at antenna gain from the perspective of this particular system. So what I'd like you guys to do is see if you can calculate a couple of things here. Let me go ahead and put this on paper for you here. The first step is to convert 20 milliwatts to its dBm equivalent. All right, you can go ahead and calculate that, put it in the chat window if you want, just send it to me. I'll pause the recording here real quick, see if you guys understand some of the things that we went through. What you should have gotten as an answer in this particular case is 13 dBm. All right, so let's go ahead and do the calculation. 20 milliwatts, remember we're always dealing with powers of or multiples of 10 or multiples of 2. So I need to come up with a number, just a decimal value, that gives me 20 in those two forms. So obviously 10 times 10 would be 100, so that wouldn't be it. But 10 times 2 would equal 20. All right? It's not a milliwatt, it's not a decibel, it's just decimal values. And if you remember, 10 is equal to 10 dB, and 2 is equal to 3 dB, right? Because it's 2 times is 3 dB. So if I take the 10 dB plus the 3 dB, 10 dB plus the 3 dB, that equals 13 dB. Does that make sense? All right. We'll go through some other examples as well, but this is one of the most basic ones I guess you can look at. Multiples of 10 and multiples of 2. You can also divide by 10 and divide by 2 as well. But every time you multiply by 2, you're going up 3 dB. Every time you divide by 2, you're going down 3 dB. Every time you multiply by 10, you're going up 10 dB. And every time you divide by 10, you're going down 10 dB. All right. So let's take a look at another example here. In this one, I want to convert 8 milliwatts. So let's convert 8 milliwatts to its dBm equivalent. I'll go ahead and pause, and I'll even leave that information up there and see if you can, based on that, can calculate that value there. All right, let's take a look at this one. So 8 milliwatts, if I go ahead and break that down, 8 milliwatts is equal to 2 times 2 times 2, right? 2 times 2 times 2 is equal to 8. Remember, for each 2, I'm going up 3 dBm. So that's 3 dB plus 3 dB plus 3 dB, which is equal to 9 dBm, because it's in reference to a milliwatt. So this would be the right answer in this particular case, 9 dBm. Does that make more sense, maybe? Maybe it's becoming a little bit more clear? All right, we'll do a few more. We'll actually do quite a few more. I want to make sure that you guys understand these calculations. Let's take a look at the third one, which is 2 watts. So now we're going to do 2 watts, and we're going to convert 2 watts to its dBm equivalent. And then let me go ahead and do another one here. Convert 23 dBm. So now we're going to go the other direction to its milliwatt equivalent. So let's try those two there. A little bit more challenging, but let's see if you can apply that concept. Okay, I'll pause the audio and let's see what you guys come up with. I'll resume my recording. 2 watts is equal to 2,000 milliwatts. So the question that I have to ask myself then is, what do I multiply together to get me 2,000? It's either 10 or 2. That's it. You can't multiply by 3. You can't multiply by 5. You can only do multiples of 10 or 2. So because 10 is 10 dB and 2 is 3 dB. So what do I multiply together to get me 2,000? 10 times 10 is 100, times 10 is 1,000, times 2 is equal to that 2,000 value. Now that I know those numbers, 10 times 10 times 10 times 2 equals 2,000, I can then convert that to its dB equivalent, right? 10 is equal to 10 dB, and 2 is equal to 3 dB. So I just simply add them up together, right? 10 plus 10 plus 10 is 30, plus 3 is 33, so it's 33 dBm. All right. The other one that I asked you guys was convert 23 dBm to its milliwatt equivalent. Well, you kind of just go in the opposite direction. 23 is 10 plus 10 plus 3, isn't it? Isn't that 23? You guys agree with that? Okay, well, 10 equals 10 milliwatts. And 2 equals 3 milliwatts. So we're applying the same principles backwards, but it's the same values, which means I add those numbers together. Now, in the case of, since we are working backwards, we can't add them, we have to multiply them, right? Just like we had listed here, multiplied the milliwatts to get the dBm, and then added these values to get the dBm. So let me actually write this out. 10 plus 10 plus 10 plus 2 equals dBm. So this is my dBm, 10 plus 10 plus 3. Now I need to multiply 10 times 10 times 2, right? Because 2 is equal to 3 milliwatts, and that gets me 200 milliwatts. 10 times 10 is 100, times 2 is 200. All right. I'm going to go through some more equations here. I'm not going to ask you guys to do them, but I do want to go through some more examples here just to hopefully kind of solidify this, and then also take a look at how this would apply you know, to antenna theory and everything else. So we're going to convert, I'll just write down a few of them here. Convert minus 13 dBm to milliwatts. That's one. Actually, let me put a dash there. And then let's say how many, and this is more of a practical application, I guess. How many dBds is a 13.56 dBi antenna? Well, let's do 13.56 dBi antenna. Right? We're talking about essentially, in this case, converting your isotropic value into your dipole value. We can do another one of those as well. How many, let's go dBds based on a 7.24 dBi antenna. So that would be another question. We can go the other way as well. dBis based on a 3.0, gosh, I can't type today. 3.0 dBd antenna. These calculations are a little bit simpler because all you're doing is adding 2.14 or subtracting 2.14. The challenge is remembering when do I subtract and when do I add, based on a 18.86 dBd antenna. And let's do one more of those. I'll just word it a little bit differently. I'm trying to think of how to word this. What is the dBd gain of a 10 dBi patch antenna? So I'm going to run through these examples. I'm still going to do a few more after that, just a couple more, because I want to extend that into EIRP and doing kind of an EIRP calculation. But let's take a look at some of these answers here. So let's start with this one here, converting 13 dBm into milliwatts. So we're still back on that, that conversion. 13 dBm is minus 10 minus 3, right? Because we're converting minus 13 dBm. So that's minus 10. And, well, I'll write it out because I want to make sure that, well, minus 10 and minus 3. Okay? It simply adds up to 13. Agreed? So minus 10 and minus 3. So minus 10, if you remember, is 1/10. So we divide by 10 of a milliwatt. And minus 3 is 1/2 of a milliwatt. Okay? So minus 1/10 of a milliwatt is 0.1 milliwatts. And we multiply that times, because when we're going to milliwatts, we have to multiply. When we're going from milliwatts to dBm, we just add. So 0.1 milliwatts times 0.5 milliwatts, oops, gosh, 0.5 milliwatts is equal to 0.05 milliwatts. So minus 13 dBm means that we're going to decrease the power by 0.05 milliwatts, if that makes sense. All right, this one's a little bit more challenging because you're kind of working with weird numbers, but you'll notice how we always are working on those boundaries, right? 13, 10, 20, whatever. And that's what they'll do on the exam as well. They'll kind of have you calculate these values, but it'll always be based on powers of 2 and powers of 10. This one here, how many dBds is in a 13.56 dBi antenna? If you remember, if you have dBi, you subtract to get dBd. If you have, the way that I remember is dBd is you delete, and dBi is you include. I don't know if that's an easy way to remember it or not, but that's the way I've typically remembered it. So dBd, we're deleting the 2.14. dBi, we're including the 2.14. So we've got 13.56. And all we simply do is go ahead and add the, or subtract, because we're calculating dBds. dBd equals, this is, remember, our dBi value. So we're going to subtract 2.14. To calculate dBds, we delete 2.14, which is going to be equal to 11.42 dBi. All right? Sorry. dBd. We were calculating dBd there. All right. Again, calculating dBd means I'm going to subtract. So dBd is equal to 7.24 dBi minus 2.14, which is going to equal 5.1 dBd. All right. Let me delete some of these. I think those, you, as long as you can remember when do I add and when do I subtract, I think you guys are okay with that. It's just a matter of when do I add or when do I subtract. Like I said, dBd, if you're calculating dBd, you delete 2.14. If you're calculating dBi, you include 2.14. That's kind of the way to remember it. All right. Looking at dBis based on 3 dBd. So again, I said dBi means we include 2.14. So I've got 3.0 dBd, and I'm going to add 2.14, which gives me my 5.14 dBi. Same thing here, dBi based on 18.86. That's dBd plus 2.14. I did the same thing again. That's going to equal 21 dBi. All right. Now this one's a little bit more challenging because in this particular case, they asked us what is the dBd gain of a 10 dBi patch antenna. Well, in reality, it's not actually more challenging because even though the question's worded differently, the reality is all we're doing is the exact same calculation. dBd means that I'm going to delete or discard the 2.14 equals 10 dBi minus 2.14, which is going to equal our 7.86 dBd. All right. Hopefully that makes sense. Maybe a little bit easier to understand than doing some of those other calculations. By the way, you guys can always go back and look at these videos and watch them over and over and over again till your head bleeds, but maybe that will help solidify some of these concepts. From a practicality standpoint, not really something you have to concern yourself with too much. You know, in the real world, we don't typically deal with having to deal with these calculations, but let me do 3 more things here. Which antenna has more gain? 2.14 dBi or 3.28 dBd? Okay, we'll see about that. Obviously, we just have to convert one to the other, you know, have a common value. Which antenna has more gain? 3.41 dBi or 4.18 dBm? And lastly, which antenna has more gain? I'll just put more gain, 4.18 dBi or 3.41 dBd. This one is supposed to be dBd, sorry. So all three of these obviously are going to be calculated the same way, but again, not something you really necessarily have to concern yourself with. I guess this might pop up. These calculations might pop up if you're comparing antennas from multiple vendors and they're referencing the gain of the antenna in different formats. So you kind of have to be able to identify the difference between them, right? All right. All right. So let's start with the first one here. We have to kind of go through a couple of different calculations here. So if you remember from our discussion, 14 dBi is equal to 0 dBd. All right. So 3.28 dBd is equal to 5. Sorry, I don't know why I wrote 14. I meant 2.14, right? Remember we add or include 2.14 if we're going to calculate in reference to a dBd. So 3.28 dBd is equal to 5.42 dBi. And we're just simply adding the 2.14 on top of that. All right. So clearly 3.28 dBd is much more powerful than 2.14 dBi. Does that make sense? You look at it and say, well, it's twice as powerful. It's almost twice, the difference is 3.28 dB, which is more than twice the power, actually. More than twice the power. Okay. Next one here. Again, we can't really convert 3.41 dBi directly. I mean, mathematically, I suppose you could calculate it. 3.41 dBi is equal to some value of dBd, but dBms cannot be converted to dBi or or dBd, right? dBm is an expression of power as a reference to milliwatt. dBd and dBi compares powers with antennas. So in the case, I think I wrote this, I changed this, and I meant to keep it that way because I wanted to explain this concept, 4.18 dBm. And there's no real direct way to compare a dBi to dBm because they're two completely different values. So is this something that we could possibly answer? And the answer is yes, we can. We just have to do some other conversions. dBd and dBi, remember, are power comparisons in reference to an antenna. All right? If the second value is 4.18 dBd, that comparison would be very, very simple. It'd be twice the power, just like we saw in the first example. But we can't do the conversion here in this case because there's no way to compare dBis to dBms. The last one, very simple, 3.41 dBd is more powerful than 4.18 dBi because there's going to end up being a difference of about 1.37 dB, about 1.5 times the power. And we do this calculation the same way, including either extracting the 2.14 from here or including the 2.14 in here to give us the difference. Does that make sense? Very confusing, I understand. Takes a little practice to get used to, but I think in the end you guys will, if you go back and review this video and kind of write things down on paper, you guys will be able to figure it out. All right? But that does conclude this particular lesson. And let's just kind of summarize what we talked about here. 1 watt represents 1 joule of energy per second. 1,000 milliwatts, of course, equals 1 watt. Decibels are used to compare relative powers. We went through a whole discussion of that. dBm compares milliwatts. dBd is power in or gain in relation to the concept of a dipole antenna, and dBi is gain in relation to an isotropic radio antenna. RF math generally calculates using values of threes, or the rules of 3s and 10s. 3 dB being twice the power, 10 dB being 10 times the power, and so on. So I think you guys will be good. If you go back and review this, you guys will be pretty good on this for the exam. You'll be able to do these calculations. Okay.